one. Let's see, last time we introduced this concept of splitting field, right? And so if we have some polynomial, I'm using f of x, so f, right? So if we have a polynomial f in k bracket x, then L is a splitting field. And I'm just sort of going to paraphrase what the precise definition is. A splitting field for f over k if, so first of all, we need f to split completely into linear factors, right, over L. So if f equals, let's say c some constant times x minus alpha 1 dot 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 x minus alpha n, where each alpha I is in L, meaning that these linear factors right here are degree 1 polynomials living in L bracket x. And so fine, it needs to split, but it needs to be, when we call it the splitting field, or I'm saying the splitting field, I shouldn't say that yet, a splitting field. So we'll say, and if we have an intermediate field over which f splits as well, right? Then actually L prime has to equal L. So if, so we'll say, and f, I'm just going to say, well, no, I'm not. I'm going to say f equals c prime x minus, well, how did I word it now? Yeah, okay, I should just say splits, right? I can use the term splits. And f splits over L prime, then L prime equals L. I forgot that I defined the term splits. So anyways, okay, so anyways, there's a quick paraphrase of, well, it's almost not a paraphrase, it's almost exact. There is what it needs to be a splitting field. Sorry. It's Friday. I got office hours in 45 minutes, so I need to get through this lecture. This is what happens, right? I'm cooped up in my office for hours, looking at Zoom, talking on the phone, or texting, or emailing, right? With no human contact, then I sometimes get a little loopy. Okay, so here we go. Let's prove something now. Now, what we have here is this sort of abstract notion of splitting field, and now what we're going to do is actually so that, there's a fairly obvious, logical, concrete way to come up with a splitting field. So this is theorem 2.1. Let L over K be an extension. And what do I need? A polynomial, I suppose. Yeah. F in k bracket x. So if f splits over L as f equals c times x minus alpha 1 dot 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 x minus alpha n, right? So that means all those alphas live in L. Then K adjoin alpha 1 up through alpha n is a splitting field. For f over k. So what this is saying is, if you have an extension, L over k, and L contains all the roots of the polynomial f, then you don't actually need necessarily all of L. All you need to do is take k and adjoin the roots, and that's going to be a place, clearly, where the polynomial splits, and it actually turns out to be the smallest place where the polynomial splits. So, so for the proof, and this proof is not particularly difficult, so what we have then, right, we know that f is going to split over this field. So, we'll say since F splits over K adjoin alpha 1 up through alpha n. All right, we know it splits over L like this. Well, then all we need to do is have the roots, and we'll have polynomials in here. Degree 1 polynomials living in here. So what do we need to do then? We need to prove this minimality part right there. So we must show that F does not split over any smaller field, or over any smaller, I'll put that in quotes, smaller subfield. Of L. Okay, so I don't know why I called it. Okay, yeah, so suppose there exists, so I called it K prime, so suppose there exists some K prime sitting in between alpha 1 and alpha n, and that F splits over K prime as F equals C prime times X minus alpha 1 prime dot 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 X minus, I used an N here, so let's use something else, alpha M prime. Now, okay, fine. We know that K adjoin all of this stuff lives inside L, which means that K prime is a subfield of L. Which means that this factorization right here is happening in L bracket X. And so is this one. And then L is a field, which means that L bracket X is a PID, which means that L bracket X is a UFD. So since L bracket X is a unique factorization domain, what do we know? We know that, first of all, the number of factors in this factorization has to match. So M has to equal N. So we have M equals N. And also now, these factors are going to agree up to units. But notice, we pulled all the units out and made all of our polynomials, all of our factors, monic polynomials, which means that they're going to match directly. So we have M equals N, C equals C prime, and up to ordering, of course, up to ordering. Well, let's say it like this, alpha, up to ordering. Each of the x minus alpha i's has to equal an x minus alpha I prime. So up to ordering, x minus alpha I equals x minus alpha I prime. So what does that tell us then? So it follows that each alpha I, which we know is alpha I prime, has to live in K prime. And so what does that tell us then? Well, all these alphas here live in here, which means that we can get containment in the opposite direction. So we can say, and so K adjoin alpha 1 up through alpha n is contained in K prime. All right, so that tells us then that we've got a smallest subfield, or that K adjoin alpha 1 through alpha n is a smallest subfield over which F splits, which means that it is a splitting field for F over K. As a quick corollary, so if L is a splitting field for F over K, then L over K is, L over K is a finite algebraic extension. So, for the proof, if alpha 1 up through alpha n in L are the roots of F, then we know that a splitting field is obtained by adjoining the roots to K. But if L is a splitting field, that tells us then that L, right, it's got to be the smallest place over which it splits, L has to equal K adjoin alpha 1 through alpha n. So then L equals K adjoin alpha 1 up through alpha n. Oh, excuse me. Now, each of these alphas is a root of F, which means that each of the alphas is algebraic over K. So since each alpha I is algebraic over K, we have that, well, remember this was, I think it was corollary 1.8, is that right? Yeah, corollary 1.8 tells us that our extension that we obtain by adjoining a collection of algebraic elements is algebraic. So we have that L over K is algebraic by corollary 1.8. And so now we have an algebraic extension obtained by adjoining a finite number of roots. Theorem 1.7 then tells us that that has to be a finite extension. So now, by theorem 1.7, the degree of L over K is finite. All right, so that's the proof of the corollary. So let's think about what we have now. Theorem 2.1 tells us how to come up with a splitting field, right? So theorem 2.1 gives instructions for constructing a splitting field for some polynomial f in K bracket x, provided we have an extension L over K, where L contains the roots of f. And this is sort of a big if there. So what this says is, if you're handed a polynomial and you happen to know an extension that holds all the roots of that polynomial, great. Then just do k adjoin all those roots and you've got a splitting field. But what if you're just handed a polynomial and you know the coefficients live in some field? How do you know that there's some extension L sitting out there if you haven't already been handed it? Right? How do you know that there's a place that contains those roots? Right? So this is a bit of a problem right now, right? I mean, if we're handed some polynomial and we don't know anything about the extensions of the polynomial, or let's say the extension of the coefficients for where the, I lost my train of thought here. If we don't know the extensions of the polynomial ring for which we're drawing the coefficients for the polynomial, that's what I meant to say, then we're stuck. What do we do? Who do we adjoin? Because we don't know where these alpha, we don't know who these alphas are. Right, so I guess let's ask this as a question. How do we proceed if we are only given this information, f is some polynomial with coefficients in k, period. We're not telling you who L is, right? How do you know there is such an L? Well, this next theorem, and this is a very famous theorem. So this is what, 2.3? Yeah, 2.3, and it's due to Kronecker. Uh, 1887. So when you hear, I mean, Kronecker obviously proved lots of stuff, but when people say Kronecker's theorem, this is typically what they're referring to as this theorem right here. So this is a famous one. So goes like this. Let's let f be irreducible over k. And I guess I should have, let's phrase this so that we know who we're talking about. So let's let f in k bracket x, so it's got coefficients in the field, be irreducible over k. And let's be specific about who the degree is also. So then where the degree of f is equal to n. Then there exists an extension L over k, and an alpha in L, such that two things happen. I mean, the first thing is that this will be a degree n extension, so such that 1, the degree of L over k is equal to n, and more importantly, f of alpha is equal to 0. That's the important part. I mean, it'll be nice to know the degree of this extension. But the thing that just happened here, you start off with a polynomial, and over here we were saying, well, how do you know there's a place where the roots live? Well, guess what? This theorem gives you an extension that contains one of the roots. Then you can iterate this process and find all of the roots, or find a place that contains all of the roots. So this is a big deal, right? This answers this question. How do we proceed? Well, we run Kronecker's theorem. Kronecker's theorem will generate an extension that contains a root of the polynomial. Okay, now this proof is fun, so let's just enjoy it. So, let's see, what do we need? We need a field. We need an L. An L needs to contain this root. Well, what do we have? We have an irreducible polynomial. And one thing we know, if you have an irreducible polynomial and form the ideal generated by that irreducible polynomial and then take the quotient, you get a field. So we're going to define L equal to K bracket X mod F, or mod ideal generated by F. And let me say a little bit more, or keep going with the sentence. And now here's the thing. Here's the part that's a little bit weird. K is a field, sort of sitting off here on its own. And then L, yes, L is a field, but as it stands, right? I mean, this right here is a quotient ring. And so the elements in this quotient ring are not exactly, they're not elements of K. So it's a little bit awkward at first, and so we have to remember, oh, an extension does not require that the base field, right, when you do this, it doesn't necessarily mean that K is a subset. K just has to be isomorphic to a subset or subfield of L. Right? And so what we're going to do is we're going to show that that K is isomorphic to a subfield of L, and within that subfield there is then in L there's a root to the corresponding polynomial. All right, so let me just write up the details now. So let's say, and let I, what I need though is a way to view K as sitting inside L, and this is what's about to happen. So let's let I from K to L be the composition and so the composition goes from K, it's a two-step process here. So we can think of K as sitting inside K bracket X just by inclusion. I'll write that down, so that's a little mapping J, and then Q into the quotient. So where J is inclusion, right? We can think of K as sitting inside K bracket X as the constant polynomials, and Q is projection. Often we refer to this as natural projection. So it takes a polynomial, let's say little g, let's say projection, so Q of little g equals g plus the ideal generated by F. So Q takes a polynomial to its corresponding coset. Okay, so I guess that was one long sentence there. So now, let's see, what do we need to say? Well, of course, since F is irreducible, L is a field. What else do we need to say? Oh, I need to argue that I is actually a monomorphism. Remember, an extension is a couple of fields together with a monomorphism that allows us to view the domain as sitting inside as a subfield of the codomain. So if I of K, see, I of K is going to be, well, little j just takes little k to little k, so this will be Q of K. Oh, no, dang it, I knew it, and I wrote it last night. in my statement of Kroneker's theorem, I need to make sure that I'm not looking at a constant polynomial. Dang. Okay, so I'm sorry. In there, so what do we have where I said with the degree of f equal to n, I needed to specify that that n is greater than 0, right? I don't want it, obviously, a degree 0, a constant polynomial, is not going to have a root unless it's the 0 polynomial. So sorry, insert that right there because I need to be working with non-constant polynomials. When I was writing up my notes last night, I wrote it and I forgot to put that the polynomial is greater than or equal to 0, and then I got stuck here for a second, and then I realized, oh, or I guess I got stuck right here, and then I realized, oh, of course, I need my polynomial f to be non-constant. And here's the reason, because this is going to be k plus f, or ideal generated by f. That's what q does. And if this is equal to 0, right, if it's in the kernel, then because we know that this degree of f is 1 or greater, this can only happen when k is 0. So then k equals 0 because the degree of f is greater than 0. And so I is a monomorphism. Okay, so that means, so we can say thus, we have an extension, and here I'm going to use the triple notation just to make it clear now. So we have I, comma, k, comma, l, and we can view k, or no, so then we have, let's say it like this, and we have k isomorphic to I of k, which is an honest subfield of k. Not k, of L. Okay, so that's the idea then. We want to think of k as sitting inside this quotient ring right here in the obvious way, right, by making use of I. So, that is, we identify k with I of k. And what is I of k? Well, it's things of this form: constant polynomial plus ideal generated by f, and view f as a polynomial with coefficients in I of k rather than k. So, okay, fine. So now we've got our L, that's the extension, and now we're supposed to, well, we'll need to argue that the degree of L over K is equal to N, and we need to produce a root, right? So here's the root. So let's define alpha equal to the polynomial x plus the ideal generated by f, right? So where does this live? This lives in, it lives in I adjoin k bracket x. There we go. Yeah, sorry. Is that right? Oh, no, okay, never mind. It lives in L, of course. No, sorry. This lives in L. Now, let's write out our polynomial. So if rewrite f. Now I'm going to write it as if the coefficients live in k because it gets a little bit clunky. So f equals a0 plus a1x plus dot 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 plus a n x to the n. Here I'm writing it just for now in k bracket x, and we'll go back and forth between thinking of it as k in k bracket x and in k or I of k bracket x. So then, if we look at f of alpha, okay? So now I want to plug alpha into this polynomial, and that's going to be f of x plus the ideal generated by f, which is equal to, okay, so now I want to think of things as happening inside I of k bracket x. And so it's going to look like a0 plus ideal generated by f, right? That is I of our first coefficient, plus a0 plus ideal generated by f. And then I'm going to substitute for x, I'm going to substitute x plus f. Or ideal generated by f. Plus dot dot dot. And you go all the way down. Eventually we get to a sub n. So it'll be plus a sub n plus ideal generated by f times x to the n plus ideal generated by f. That's equal to, so let's see, what is this? This is q of a0 plus q of a1 times q of x plus dot 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 plus q of a n q of x to the n. And then q is a homomorphism, so we can combine this all into one thing. So this is q of a0 plus a1x plus dot 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 plus an x to the n. Which is q of f, which is f plus the ideal generated by f. But that's the identity coset within k. So this is equal to, I'm going to write it as equal to 0. Here, this is in L, of course. So that's pretty clever, right? I mean, that's the genius of Kronecker right there, is that alpha right there. Noticing that alpha, when plugged into the polynomial viewed as sitting or having coefficients in I of k, actually is a 0 of the polynomial. Okay, so that takes care of part 2. So we have proved part 2. And so now we just need to look at the degree of this extension. So now consider well, what we have is I of k. What do I want to do? I want to do I of k adjoin alpha. I of k adjoin alpha. I know this notation looks a little bit messy, but what we have, I of k is a subfield of L. Alpha lives inside L, so we can adjoin, right, alpha to this subfield right here, and that's all going to be happening inside L. Now, elements of L are of the form, so what do they look like? They look like cosets where the coset representatives are polynomials. So they look like, what did I use here? B's? Yeah, B0 plus B1x plus dot 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 plus B sub something, don't use n, so Bm x to the m plus the ideal generated by F. And this is equal to B0 plus F plus, ideal generated by F, plus B1x plus ideal generated by F plus dot 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 plus Bm x to the n plus ideal generated by F. And then I'm going to actually expand this a little bit further. So this is B0 plus ideal generated by F plus B1 plus F, just using what it means to multiply cosets now, x plus ideal generated by F plus blah, 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 plus Bm plus ideal generated by F times x to the n plus, plus ideal generated by F. And where does that live now? Well, this lives, right? This is a polynomial. Oh, and I guess I should, let me put the n up there like this. So where does this live? This lives in I adjoin k right, it lives in I adjoin I of k adjoin alpha, right? Alpha is x plus ideal generated by F. All right, so this is just a power of alpha. This lives in I of k, and so on down the line. And so what did we just show? We just showed that L is a subset. And so L is contained in I of k adjoin alpha. Okay, so now we know that L is equal to this right here. Also note that alpha is algebraic over who? Over k, right? I'm getting lost. Oh, yeah, over. Well, okay, technically it needs to be over I of k, which we know, right? We're sort of equating that with k. Now, by this is theorem 1.5. The degree of our extension, L over, okay, officially it should be over, it's set theoretically it should be over I of k, but we're going to write it as L of k. So by theorem 1.5, the degree of the extension is equal to the degree of the minimal polynomial for alpha. Now, since since F is irreducible over K. Now, what do we have? We know that that the minimal polynomial is just a monic version of F, right? Pull the main constant out and then divide it away, and you've got the minimal polynomial, right? So what does that tell us then? It tells us that the degree of the minimal polynomial is exactly equal to the degree of F, which is equal to n. So we have that the degree of m sub alpha is equal to the degree of f, which is equal to n. So that tells us then that our extension here, it has degree n. It's pretty slick, huh? Let's see how we're doing on time. Well, let me just, there's a quick corollary here. Let me just finish off with this corollary. But one thing to notice, Kronecker was very big on constructibility, right? He didn't like this idea of abstraction, right? In fact, he and Cantor were, I don't know if you want to call them enemies, but he was somewhat of a tormentor of Cantor, right? So Cantor had this whole theory of abstract set theory. Cantor was very opposed to it. He wanted everything to be constructed. So here we have this sort of abstract notion of fields, right? And it's his proof. It's his proof here. So as a quick corollary, so this would be corollary 2.4. If f in k bracket x has degree n, then f has a splitting field. So f has a splitting field, say L over k, where the degree of this extension is less than or equal to n factorial. And here's the proof. What we did when we proved Kronecker's theorem, we set it up where f was an irreducible polynomial. So what if it's not? If you start off with a polynomial f that is not irreducible over k, well then break it up into its irreducible factors. So let's say decompose f into irreducible factors in k bracket x. So split it up as far as you can, but only into polynomials that still live in k bracket x. So then what you do, so we'll say then apply Kronecker to each factor, say inductively. Okay, so there's a good place to stop. What we have now, this proof right here, this corollary, gives us the existence of a splitting field for any polynomial, right? And it follows directly from Cantor's theorem. Okay, and by the way, it's kind of ugly, right? Our construction like this, where we happen to know who L is beforehand, is much nicer, right? Because you're going to have quotient of a quotient of a quotient of a quotient, right? The number of quotients equal to the number of irreducible factors, right? So Cantor's theorem does not give us a nice solution, but it does tell us that the solution always exists. There is always going to be a splitting field. Okay, so we'll see you next time, right?